thanks, Paul, for the introduction. And first of all, I would like to apologize for being late. I had a hard time finding the auditorium and so on. I was never here in this part of Poblenou, but I have to say it's really a beautiful venue. And it's really a pleasure to have the opportunity to tell you about very recent experiments that we have been doing in quantum simulation, in analog quantum simulation, in my group at ICFO in Casteldefels, so very close to here. So what I want to show you is how we can use neutral atoms, like the ones that Gerard was talking about before. You can see here, I'm an experimentalist, so I like to show experimental pictures. You can see here an image of a cold atom cloud here of strontium atoms that is shining inside an ultra-high vacuum chamber. And how we can now build new experimental tools, in our case, this microscope that is here, to just take images of these atoms, really atom by atom. And then what is new in what I will be showing you is that we can do that now for up to 10 different spin components. So it's a very unique system that we have here. So in general, in my group, we are interested in quantum many-body systems that can be inspired from liquid helium, from materials, from quantum gases as we do. And we are interested in the emergent phenomena that come here. Because we can use these quantum many-body systems for really solving or try to address hard quantum problems. Really the guiding line of a lot of our research, and certainly of the research that I will be showing today, is the idea that we could try to replicate the phase diagram of strongly correlated materials like this levitating high TC superconductor that you see here, that have this conjectured phase diagram. This is a phase diagram that is conjectured because already doing numerics on this is very hard, and there are really many competing approaches and different results that go around, where people believe that, okay, there is a model, a so-called Fermi-Hubbard model, that should show high TC here. Yeah? And then the question is, okay, we cannot solve these problems on classical supercomputers like the Mare Nostrum here in Barcelona, but we can follow Feynman's approach of building a quantum machine with which we could imitate that and really try to get the answer. And our quantum machines look basically like this. They are running in a room a bit smaller than this auditorium, but half of it, not more, and they are full of laser beams and electronics and so on. And what we do there is we take atoms like the air that surrounds us in this room, that is hot. Initially, our atoms are really behaving very classically, and then we cool them down with laser cooling and also evaporative cooling to temperatures such that the wave packet associated to each of these atoms becomes larger than the distance between particles. We enter quantum degenerate regime, which happens for us at temperatures of the orders of tens of nanokelvin, and then we get quantum gases. And once we have these quantum gases, we really have quantum matter that we can control very well at play, with which we can engineer different Hamiltonians and different models. I like to always show this picture because this is the first Bose-Einstein condensate that we made in my group, the very first time that we took these atoms and we cooled them to the quantum degenerate regime, which was really, I mean, by now, 10 years ago, a bit more than 10 years ago. And these type of results, they are obtained in these labs. So, as I say, I'm based in the Barcelona area. I'm based at ICFO, which is in Casteldefels. So this is now, we are here in Poblenou. That's why I also took some time to come, because there were a lot of traffic jams. It's really the opposite extreme of Barcelona, and if you came to the airport, it's quite close to the airport. And in my group, we have different experiments on quantum simulation using ultra-cold atoms. So we have my first lab, which is what we call the potassium lab, because of the atom we use in there, that investigates mixtures of Bose-Einstein condensate. So that's where we made the first Bose-Einstein condensate in Spain. But we have been doing a lot of different quantum simulations with that, from investigating quantum liquids, so this is physics that has link with liquid helium, to realizing gauge theories, or our most recent results, they are on super solid phases of matter. Then we have a Rydberg lab that actually is very close to things that Gerard was presenting in his talk, because what we are building is a Rydberg atom array machine that will use these Rydberg gadgets that he was describing, actually to try to tackle the challenge of engineering 2D lattice gauge theories. So really we want to address problems from high energy physics in these platforms. So we have well-defined proposal for that and so on, but our machine is still under construction, so we can have, we can see by now cold atoms, but not yet engineer these models. And then we have a third lab, which is what we call the strontium lab. This is the atom that we use in there. That is what I will be talking about today, which is our Hubbard quantum gas microscope, where I will be presenting mostly results that are in this paper and also a lot of unpublished new results that we are about to finish writing now. So in this lab, we call it the strontium lab because of the atomic species that we use, because if you use neutral atoms for quantum simulation, actually the atom that you choose can play an important role. At the end, these are always quantum particles, so the models you would say, well, maybe should not depend on the atom that you use, but different atomic species, they give you different ingredients with which you can engineer different Hamiltonians. So we use here strontium. You see here the theme that is all pointing to this element, which is an alkali-earth element. So it's second column of the periodic table. So that gives it 2 valence electrons. So you have the ground state, and then you have 2 sets of different excited states, depending on whether the 2 electrons are put in a singlet or in a triplet configuration, and that gives you 2 sets of optical transitions, one in the blue and one in the red. One is broad, one is narrow to atomic physics standards. This broad or narrow depends of the compared to the width of the excited state, basically. And then this atom has also this super narrow optical transition, which is a so-called clock transition. It has millihertz line width, and this is used for metrology. So now having an atom with these different sets of transitions is beneficial because you can exploit them for engineering different Hamiltonians. It's also an atom that we like because it has 4 stable isotopes. It has 3 bosons and 1 fermion. And at ICFO we are using 1 bosonic isotope of strontium and 1 fermionic one. And that means that if we want to do quantum simulation experiments, depending on which isotope we decide to put on our machine, then we can mimic either bosonic or fermionic systems. And then what will be a lot the topic of my talk today is that when we take the fermionic isotope, it has a nuclear spin of 9.5. So it has 10 spin components in its ground state. And this is a fantastic resource for quantum simulation, and will also be a fantastic resource for quantum computing if we decide to go in this direction in the future, because you will not have qubits anymore, but qubits. You have really much more components here. Because of these features of strontium that I just showed you, the different sets of optical transitions and these 10 spin components in the ground state and the fact that you have bosons and fermions, strontium finds a broad range of applications in the field of quantum technologies. So one of the most known ones is in the field of metrology. The most precise atomic clocks right now in the world, they are made with strontium atoms because you have this very narrow optical transition that you can use to interrogate frequency very precisely, and that's time. And these are, for example, very impressive experiments from the group of Yunye in Gila, in Colorado, where they can actually see the gravitational redshift, checking how the clock ticks differently a few, like less than a millimeter apart in 2 parts of an atomic cloud. But you can also use that for atom optics and for making basically laser sources basically for these clocks using these strontium atoms. Then you can trap these atoms in optical tweezers, like the tweezer arrays that Gerard was discussing before, and use them for quantum computing or also for quantum metrology. And there have been actually nice demonstrations of quantum and digital quantum computing with strontium. You can use that also for quantum optics experiments and for quantum simulation, which is the topic that interests my group. So in my group, we are interested in using strontium atoms for quantum simulation, really with the idea of simulating materials. So to simulate materials, we need to simulate the electrons on the material. So we take quantum degenerate fermions, and then the crystalline structure of the material, which is the periodic potential, which we do by putting ultracold strontium atoms in our case, strontium-87, which is the fermion, to get closer to the fermionic nature of electrons, and interfering laser beams to create a crystal of light that will play the role of this optical lattice. And the whole idea at the end is that we get this quantum degenerate gas that we cooled so much to nanokelvin temperatures, and then we put it in a structured potential such that it looks like a solid. So this is the vision, then in practice the experiment looks like this, and then you cannot see the optical lattice because it's made with infrared laser beams, but basically you have to believe me, here we have an arrangement of beams that just go in this kind of bow tie configuration, which make an egg carton for our atoms in here. And actually this is the picture of how our system looks like. So the gray thing is the optical potential for our atoms, and the blue are the atoms. So we have this 2D optical lattice and the ultracold atoms, and we confine our atoms to also lie only in one plane. So now this looks very much like a material, but if we look at the relation to real solids, energy scales are completely different because we live in this nanokelvin world, while solids live in the electron volt energy scale. Spin degree of freedom in solids, you have the spin of the electron, and you may have in some materials some pseudo spin. For example, in some 2D materials, graphene-like and so on, you have a valid degree of freedom. Well, here we can have many internal states of the atom, so we can go beyond that paradigm. Then interactions, in our case, interactions arise when atoms occupy the same lattice site through collisions between the atoms. And then we can adjust a lot of the parameters here by changing the intensity of the laser beams, for example, to make the potential deeper or shallower, or changing the number of spin components. So what we build ourselves in this way is a quantum machine to simulate solids. And if you look at the key ingredients that 2 electron atoms like strontium bring you, is that you can introduce in a very nice way dissipation with these narrow optical transitions. So you can investigate not only Hermitian dynamics, but also non-Hermitian one, dissipative many-body systems, where there have been quite some nice demonstrations in the field over the last years. You can couple the internal states of the atoms with lasers and use that to engineer artificial magnetic fields that can be very strong, and then try to emulate the physics of quantum Hall systems, fractional quantum Hall physics, and so on. Or you can, for example, try to look at Hubbard models, so these toy models, but with more than 2 spin components, which is really what I want to tell you about today, because this is currently the main focus of our research. So basically, I told you, I mean, using cold atoms in optical lattices has really, for many, many years now, this idea of trying to replicate the physics of strongly correlated materials, and specifically of high critical temperature superconductors. So the model that we aim at replicating, that actually our systems realize very well in the lab, is this Fermi-Hubbard model that describes fermionic atoms that can hop from site to site on an optical lattice. Yeah, they tunnel from one side to another. This is with this matrix element T for tunneling. And then when you have 2 different states, when they occupy the same side of the lattice, they interact repulsively. Okay. Okay. They interact repulsively with an interaction energy U. And when you check this model, everyone tells you, well, we believe that this model, or small variations of this model in 2 dimensions, will have high temperature superconductivity. Okay. So basically, this is this part of the phase diagram here. Now, what we are interested in doing is to check this model, but instead of just having 2 spin components, putting much more of them, that we can go as high as 10 with strontium. Okay. So I will try to move my mouse or something like that, that this does not happen anymore. And why would we want to do that? Well, if we checked, actually, the Fermi-Hubbard model with 2 spin components is already a very complex model to solve classically. So we don't know well how to solve it with classical computers. So my students like to say, well, this is like playing Go. It has 2 types of stones, and this is already a very rich problem. Now imagine the richness of playing Go, but with M&Ms, with many colors. It gets even more complicated and richer. So actually, we can really go far beyond what classical machines can do much more quickly, basically. Yeah? So this is really one of our motivations to look at this model. And we are, of course, not alone. So there are different groups in the field that have been looking at these SUN Fermi-Hubbard models over the last years. Here I summarize some results that are really pretty recent, looking at the equation of state of these systems, at what happens when one breaks the symmetry. And actually, this I was a bit too fast here because I was worried that my screen was going away. So not only do we have 10 spin components in this model, but on top of that, we have interactions that are identical between all these spins. So this gives the model what we call an SU-N symmetry, where N will be the number of components. So then you can also break this symmetry and see how the phase diagram of the system changes. And then you can do something which is what is closest to our research, which is to investigate magnetic ordering in such models when you go beyond 2 spin components. So this is really actually what we want to do. So basically the idea of this Hubbard model is that when you just look at it with these 2 spin components, if you are at reasonably high temperatures, then the system does not order in any way. So you can have sites that are simply occupied, sites that are doubly occupied. You can have holes, yeah, with no kind of order. That's when the temperature is larger than the interaction energy for 2 atoms in a given site, then the system is said to be metallic. Then if you cool it more down, at some point you will have interaction-induced localization, enter what is called a Mott insulating phase, where basically for the atoms it becomes energetically favorable to localize in their lattice sites, because if they occupy 2 different atoms the same lattice site, they have to pay this interaction energy use, so that costs a lot of energy. And then if you cool even more down the system, at some point it becomes energetically favorable to order them antiferromagnetically, because this reduces the kinetic energy through so-called super exchange processes. So these are things that we can nowadays do very well with neutral atoms in optical lattices. And what you can see here are very beautiful images of actually one of the spin components in an optical lattice taken with techniques that I will show in a moment. That's what is called quantum gas microscopy, where you can really see in each lattice site where an atom is or not. And then you see here they really occupy 1 atom per site. And here, if you only image one of the components, you really see that they arrange in this checkerboard pattern. So you really see this magnetic order directly. Yeah? So now, why would you want to go beyond these 2 components to more components? Why is this problem richer, or why is this problem classically harder to compute? Well, this is because SU2 is a very special case. It's what is called constrained magnetism, because if I now put 1 atom, for example, red in this site, when I put an atom next to it, okay, it will be blue, and then the blue next to it will have to minimize the energy of the red, and that will go on. So basically, there is a single way of arranging the atoms once you fix the position of 1. Yeah? But if you go with more than 2 spin components, for example, already in the very simple case of 3, then you can fix the position of the first atom, but now you could minimize already more or less the energy in the same way. I mean, certainly the same way if the system is SU3, the interactions are the same by putting green or blue. And then once you put green or blue, you can again have different choices of what you put next to that. So that's telling you that actually there are many different possible arrangements that are going to have very, very similar energy. And then there will be very small differences between them that will lift the degeneracy. So that tells you that this is a much harder problem to compute because the problem is what is called unconstrained. Yeah? So actually, if we check the Hubbard model in its most strongly interacting limit, then it becomes a Heisenberg model, like a spin model, spin Heisenberg model. And we know very well how spin 2 Heisenberg model works, like with spin 1/2 with these 2 components. But now if we look at 3 components, we can already find what's the ground state of the system. So of all the arrangements that I was showing before, what we know from pretty tough numerical simulations is that it's this diagonal order that is favored, even though the others have very close by energies. For n equals 4, we know that actually it's this checkerboard order where each of these things is actually a singlet of spins that is favored. If we go to n equals 5, there is this fun order that looks like a knight move in chess. Yeah? But then if we go beyond n equals 5, it's not even clear that there is a preferred order, because there's so many competing configurations that are there have led to predictions of spin liquid phases in here. So this is already very rich, and this is in the very strongly interacting limit, where the model is much simpler than this Fermi-Hubbard model, because there is no itinerance, there is no hopping, atoms are just spinning their sides. So if we now restore itinerance, even the simplest SU3 case becomes very complicated, because this diagonal order is only valid for the very large interactions. If we go to less large interactions, what has been predicted is that we have zigzag phases that appear, and different zigzag phases depending on the exact value of the interaction strength. And there is nowadays even quite some debate in the community, because depending on the numerical method that you use, you find different zigzag phase for some interaction parameters. So that's already an open problem. And then if we go to SU4, then we really don't know what to expect. And the same if we just start putting, this is for on average 1 atom per site. If we start putting a bit too many atoms or too many holes, that's what is called doping. That's where high TC is supposed to appear. Then if we do that for SU3, there is already very rich physics also beyond the SU2 paradigm. So this motivates us actually to build an experiment to look at SUN magnetism. And we want to do that being able to see every single atom in their lattice sites and every single spin, because that's the good way of basically getting all information from the system. So we want to look at SUN magnets under a microscope. And this actually brings me to the topic of my talk, which is how we can build these SUN microscopes. Because I told you before, but I want to show you a bit better now, that actually when we trap atoms in optical lattices, we can do things in a way that we can image every single atom in their lattice site, which would be like in a material imaging every electron in a solid. And actually we can do that in a single shot. And we can do that because the spacing in the optical lattice is large enough that it becomes resolved with optical means. And this has been done by now for quite some years for different atomic species. So you have bosonic species here in the left of my screen and fermionic species on the right one. So if we wanted to do this for an SUN system, we would have to look at the fermionic microscopes, which are only 3 atomic species that have been cooled until now. And we would need to look at 2 electron atoms, which are the ones that have these many spin components and SUN symmetry. And you see that in principle, there is nothing here. Atoms there would be strontium and ytterbium. And what I want to show you is that now we have unpublished data on how we can perform this microscopy with strontium-87. So for the first time, we can make microscopy of these SUN systems. And by doing so, actually, we developed a lot of techniques that also allowed us to realize a new type of microscope for bosons also, which is a microscope for strontium-84, which is the bosonic isotope. So with this, I really come to the outline of my talk, because now I will just show you how we actually do these things in the lab and what are the ingredients that we have at play and what are the things that we can manipulate. And I will first show you how we built the first strontium quantum gas microscope in the field, which was done with bosonic atoms, which is a result that we published last year, and then show you how we can do microscopy of the fermions, and on top of that, add spin resolution to it. So let's start simple, and let's start with the bosons. How does this work? So actually, you see here an image of our setup again, with this microscope that is here. And I told you we have this lattice that goes around, yeah, that makes the potential. And then we have another beam, which is this one here, that just confines the atoms very much in a plane to have a 2D system. So at the end, the cartoon picture of how our system looks like is like this. So we have this egg carton with the atoms in there. Now, in order to image the atoms, what we are going to do is fluorescence imaging. So basically, we will prepare our system in a situation where we will be hopping interactions, the Fermi-Hubbard system that we, or Bose-Hubbard system that we want to investigate. But for taking an image, what we will do is that we will suddenly increase very much the depth of the optical potential such that we pin the atoms in their lattice sites. So we will do a projection, basically, on the occupation of the sites. Yes? Because what we will be measuring then is occupation. And then we will just send light, which is resonant with an atomic transition. As I showed you, strontium has several atomic transitions, so you have quite some choice. And then the atoms will absorb and re-emit photons, and this fluorescence will be captured by a high numerical aperture objective and an imaging system into a highly sensitive CCD camera. So if you do that, things don't work very well. Things don't work very well because actually in these optical lattice systems, atoms are very close by one to another because we need to have them close enough that they can tunnel from one side to the other. Yeah? So actually when you send light, the atoms also heat up, and then they can just move off-site, and then you would get confused because you think that they were in a location, but actually it's during your imaging that they moved from one place to the other. So we definitely need to do cooling during the imaging, and this cooling during the imaging, what it does is that it allows you to keep the atoms in their sites for long enough that you can collect enough photons in order to determine well where they are. So how we do that in our experiments? So in our first series of experiments, we thought, okay, we have strontium with different sets of optical transitions. We have a short wavelength transition, a blue transition. This is very nice because it has a shorter wavelength, so the diffraction limit is smaller. So we can see objects that are closer by, basically. So we said, let's use that for imaging. And then for cooling, we have this transition that is very narrow that actually allows to do better laser cooling. So we said, well, let's take this one for cooling, this one for imaging. And there is another wavelength that is important in this problem, which is the wavelength at which we actually do this optical lattice, which is done at this wavelength here, which is not by chance. We choose this wavelength because it allows us, it will allow us later to address this clock transition. So we actually tried this scheme, and we were super lucky that it worked basically immediately. And we could take these images of the atoms in the lattice. And here, what you are seeing is every white spot here in this image is an atom. The blue, dark blue, is the background. And we were loading a lot of atoms in this lattice, thermal gas. So basically, there is a random distribution of atoms and no atoms in the sites. That's why there are some white spots, but also a lot of dark spots, because the sides of the lattice here, they are randomly filled. Yeah? Okay, so a key ingredient for making this thing work is that this cooling works, as I told you before. And there are different ways of making this narrow line cooling of the atoms in the lattice work. One way is to use what is called resolved sideband cooling. So basically, if the atoms occupy any higher excited vibrational state of the lattice, then you can remove this energy and put them down here. For that, you need to have the same trapping between the ground and the excited state in the lattice. You can also use Sisyphus schemes, where, for example, in this one, the atoms absorb a photon in the center of the lattice, and they are more trapped in the excited state, so they travel in the excited state, and then at some point they will re-emit a photon down. And then if the hill that they need to climb in the excited state is larger than what they go down in the ground state, then they will remove some energy by doing that, and that's how you can cool. And then you can do the thing with the potentials that are the other way around, and then instead of absorbing the photons in the bottom of the trap, you would absorb them in the edge. Yeah? And these are type of techniques that have been pioneered in experiments with optical tweezers, in these optical tweezer array experiments that Gerard was describing, for strontium specifically at Caltech, at Gila, and in Amsterdam. And then these techniques could be implemented in optical lattices. And doing things in a lattice is quite trickier than in tweezers, because in tweezers the atoms are much further apart, so you are much more tolerant to mistakes, let's say. When you're in a lattice, as soon as you don't cool perfectly, then atoms can hop to the neighboring side. But still, this cooling is very efficient, and this has worked basically for all isotopes of strontium, and the black results are the ones that are published, but the gray ones are not published but are around in the field. So we demonstrated these strontium 84 results that I showed you before using attractive Sisyphus cooling. Then in the Max Planck Institute in Munich, they did this with strontium 88 using this repulsive Sisyphus, and at Gila, they used that doing resolved sideband. So really all the techniques work. So how does this work? Actually, I told you it's important that we use this optical lattice at this wavelength. What you see here is something a bit technical. It's what is called the polarizability. It's telling you how much trapped the ground state is going to be, or the excited states are going to be. And what we see is that depending on the polarization of the light that we send and the exact frequency of the light that we send at the wavelength of our lattice, we can have either a configuration where the atoms are more trapped in the excited state than in the ground, or the other way around, so we can actually implement the different schemes in our experiment as we want, just by choosing what is the exact frequency of the laser and what is the exact polarization. And we decided to use this attractive Sisyphus cooling because it looked the simplest and the most robust of all the methods. And that's how we take our images. So you see here, this is how a raw image looks. So actually, what you would like to have is to know where are atoms and where are not. So you want to build an occupation matrix, basically, out of your raw image. We use some techniques for that. So basically, we know what's the answer of our optical system to a single atom, because we can take isolated images of these atoms and get what is called the point spread function, so the response function of our optical system. So we can then use the convolution methods, like in astrophysics, basically for distant stars, to just get better information of where the atoms are. And then we get this type of deconvolved images, and then we just make basically bins in the different places, and we check how many counts we have or not in our camera. And then if we have very small number of photon counts when we illuminate the atoms, then we are basically seeing noise. Yeah? So then this is the signal for 0 atom. And then if we have high number of photon counts, then we are seeing an atom. And what is nice here is you see you have this bimodal distribution. What are the counts for no atom and what are the counts for an atom? That is very well separated, so it allows you to put a discrimination threshold here very accurately and say, okay, below this number of counts, I say it's 0 atom, so then I put 0 here, and above it's 1 atom, and I put a dot. And then the fidelity with which we can do that, in principle, is 99.9%. It's really very good. No? So then we can do that, and we can also take videos of the atoms and take many, 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 many images of the atoms and see what's going on. And that brings us to another measure of the fidelity of this imaging, because this is the fidelity that is normally used in neutral atom quantum computing and so on. You just say, okay, I can say there is no atom, there is an atom. But actually, you can be pickier, and you say, well, I take my cloud, I take an image, and then I take just afterwards another image, and I really check how identical they are or not, basically. I can do the scalar product, basically. And then what you see is that there are a few differences that can appear. You can have some atoms that disappear. These are these red events. And then you can have some atoms that change location, because if this cooling is not perfect, they are heated up, and then they can pass to the neighboring site. And then with that, we come up with a different measure of the fidelity. This is called what we call the pinning fidelity. It's really the overlap between two consecutive images. And this is above 94% for this method that we demonstrated here. And it's dominated by a few losses. And this comes from the fact that our atoms don't live forever in this lattice. I mean, after like 30 seconds or so, you see there are some that are gone. So neighboring images, they always have this type of fidelity. If we wait for longer, then this fidelity of the first image versus the last one has much more loss events, and that's why it goes down. So this was our first demonstration of microscopy with bosonic strontium atoms, which we liked, but we were not so happy that it took quite some time actually to take these images. So each of these images took up to 3 seconds to take. So we then found a different trick. Instead of illuminating with this transition and cooling with this one, then we decided to do everything with a single transition. And this also worked fantastically, and it's even simpler because you need a single laser beam to do this. We take images that look very much the same. Now we change the color scale because it's a different color of photons that we recover on the camera. So for us to keep track of that, we just put a different color. And we get also very nice histograms, actually, because we image much shorter times, about 400 milliseconds, then we have better fidelities because there are not these losses in there. So we really get images one to the next that are better than 98% fidelity. And as I said, really distinguishing these two peaks, we can do even much, much, much better. Yeah? So this is a very simple and efficiency quantum gas microscopy method. And we actually think we are now writing a paper on this, that this is the simplest quantum gas microscope that you can do with an atomic species right now in the community. So that's actually something nice, because hopefully more people will build some of these microscopes. And another thing that we can do is to put a Bose-Einstein condensate into this lattice. And in our system, we know that for our experimental parameters, we should have a superfluid in there, so we should have a system with phase coherence. So basically, we should have atoms that share all the same phase, such that if we release them from the sides of the lattice and we make them interfere, there should be an interference pattern arising. And actually, if we look in situ, we don't see anything like that. But if we look in momentum space, which we can do doing some expansion tricks, we indeed see some interference pattern that is telling us that we have a superfluid in the lattice. So this is the first time that the strontium quantum gas was imaged at the single atom level in a lattice. That's why we say we can make a quantum gas microscope, because we have quantum gases that we can see under the microscope. Okay, so this is what I wanted to show you about all the techniques for getting the atoms cooled. Now let me show you what I think is the most exciting part, which is that we can play the same tricks for the fermions, and we can also give them spin resolution. So at the beginning, we tried replicating the tricks with the two colors for the fermions, and we failed miserably. It was not working well. We know why. It's because we had these nice level structures and these nice different trapping potentials for the grounded excited state for the bosons, but the fermions are much more complicated because they have a nuclear spin. That's what gives you these 10 different spin components, but that also makes that all this cooling and so on, it's much more complicated because we can select one of the transitions here, but then we still have a lot of sublevels, so we have many transitions, and some work, some don't for the cooling and so on. So we realized that we can make things work provided we just limit ourselves to just the extreme transitions here. Yeah? And then things should work in principle like for the bosons. So that works in practice, and I will skip this, but just because strontium is a bit magic, because the hierarchy of energy scales of splittings in the excited state, in the ground state, and so on, works very well, and it works only for the red transition because the red transition is very narrow and not on the blue transition. That explains why when we try to make things work for the blue transition, they were not really working like that. So we just limit ourselves to this only red scheme, which is also simpler, so that's nice. So we put atoms in the lattice. We send this beam that will both cool and image. And then, as I said, we have a narrow transition that is only 7 kilohertz. We can make splitting between the excited states that is 3 orders of magnitude larger, 7 megahertz, and the splitting between the different hyperfine states on the excited state here, these ones, it's even gigahertz. So we can really very well not address states that we don't want. So what happens is that we put atoms in our lattice, and then there are these 10 spin components, but our light will only be sensitive to one of them, which are the red ones. Yeah? And then we can take images like this. These images, they look very nice. We can distinguish single atoms. You will see that compared to before, they are very empty. They are very empty because actually we are only imaging 1/10 of the atoms that are in the lattice. The spin component that we are sensitive to and not any of the other. So that's actually nice also because it helps us with optical resolution. Because there are much more atoms nearby, but we don't see them because we only see one of the spin components. So we get, again, very nice histograms with nice discrimination fidelities and pinning fidelities and so on. The point, of course, is that I told you, well, these systems are nice because you can see, you can have many spin components, and that gives you the magnetism, that gives you the rich phases that you cannot compute classically. So now I showed you that my imaging only works for one spin component, so it looks like the purpose of what we wanted to do is defeated. But I want to show you that this is not the case, because actually we can use that to actually do spin resolve imaging of our system. And actually, just to give you an idea of the state of the art, people have done spin resolve detection in these optical lattices, but it's really limited to 2 components up to now. What we have is now a scheme that can scale up to, in principle, any number of components. How it works is the following. So we take our light and we image one of the spin components. Yeah? And then once we have finished imaging it, we blow it away, and then we take the next spin component nearby, and we just put it by so-called optical pumping into the state that we know how to image, and then we can image this one. Okay, once we are done with that, we have the image, then we throw it away, basically the atoms. And then we take the next spin component and we just put it in the imaging transition. We image it. And then you will believe me, and so I spare you the animation, that we can do that as many times as we want. Of course, how well this will work will depend on the fidelity of each of the processes. We've characterized actually the fidelity of each of these optical pumping processes, and we find that each of them can have a fidelity larger than 99%, so this was quite positive. But still, it was last May, June that we managed to make this thing that I'm showing you here, to just take one spin component and then apply the protocol for each of them successively. And you see, we can really take images now where we are seeing and reconstructing the occupation of these 10 spin components in the optical lattice. So initially we have these 10 spin components, we see only one, but then successively we keep seeing the other spins until we just get images like this one, which we have color-coded. So each of the colors corresponds to the image basically of one of the spin states, and of course the corresponding noise. So with this, what I'm showing you is the first time that anyone, to our knowledge, sees in a spin-resolved way an SU10 Hubbard system. So that got us very excited. And then, of course, we wonder how well our method was working. Yeah? So I will go fast because I think we have almost no time left. But basically, we had the idea of trying to make a very simple physics experiment that could tell us how well our imaging was working, not just from believing us that we can calibrate our processes very well, but just some physics that shows that. And for that, we started preparing all atoms spin polarized in one spin state, and then do a quench of the magnetic field to initiate some Larmor precession. And then during the Larmor precession, all the spin states will be occupied. This is a very simple problem if the sites are decoupled, because we can compute everything. And then we can see after a while, like we remeasure in the spin basis in which state we are, how well this performs compared to what we expect from our imaging. And then what we see is that we start with all atoms in this state, and then they really start in this state. After half a Larmor period, they exchange to their spin state, and then they come back, and they can do this for really many, many periods. And we can actually take a given time. We can take images like these, where we see initially they're all in one state, except a little bit maybe of infidelities. And then here in the middle, I mean, have many spin states occupied, and then they go to the opposite one. And we can really see here what is the dynamics, and the solid lines are really what we expect from theory. There are some corridors on the solid lines that you can almost not see because the error is very small. These are the errors of our imaging, and then the points are what we measure in experiment. And it all agrees very well. So with that, we can actually say that we can image very, very faithfully these systems with fidelities which are above 90%. And now we even have some clear clues of what is still the limiting factor, which we are even working on improving. So we think we can reach fidelities as high as for the bosonic case, so above 95%. So with this, I really come to the conclusion of my talk. So I showed you how we can make Hubbard models with strontium atoms in optical lattices and do single atom and single site resolved fluorescence imaging of the bosons with two different transitions and of the fermions. For the fermions, we can do this very cool spin resolved detection. For the bosons, we can actually see superfluid phases, so we can start to do many-body physics. And then, of course, now the next step is to look at many-body physics with this SUN microscope. But I want to advertise here that imaging these large spin systems at the single atom level, all the techniques that we have developed are also very useful in other contexts of quantum technologies. So we have already been discussing with people from atomic clocks that this could be used to cross-check some processes, basically, that can be limiting in clocks right now. And then, for sure, if you want to go in the quantum computing direction with not qubits but qubits, I mean, you will have to implement some readouts. So if you do that with neutral atoms, the best candidate is clearly strontium, and I think this will be the method of imaging that will be used. Then I want to finish by showing you the team that did the experiments. So this strontium lab is a fairly recent lab, so all the people that have contributed to it are here in this picture, all the PhDs and postdocs. from Jonathan, that I think some people here at Kilimanjaro know because he was here for some time, was the PhD student that built the experiment together with a postdoc, Vasily. They really got the lab first up and running, and then they were joined by Sandra and then by Tony. So the four of them were the ones taking the boson microscope images. Then for the fermions, they were joined by another PhD student, Carlos, and then now another one, Leonardo, that have done both a great job. So the fermion results are very much theirs. And then quite some of the people have very recently actually moved to new positions. Jonathan was the first to go, and Vasily, but also now Tony has a position at the University of Barcelona. Sandra moved today. She was starting at IDEADET, where several people from my group are actually setting up neutral atom activities. And then we have a new postdoc joining together today the group, and also visiting students from other universities also contributing to our research. So I really have to thank them very much for the great job, because without them we would have nothing that I showed you today. And then I also want to show you my group and theory collaborators, and thank you very much for your attention.
Okay, we have time for questions.
Hi, thank you for the fantastic talk. Sounds weird. Have you considered maybe simulating some of these like SU8 Fermi systems you might find in like twisted bilayer graphene, for example, where like you get the valley, spin, and layer symmetries, so you can look at some of these like spiral Kekulé order stuff that they've imaged?
So that's a very nice suggestion. We didn't yet, because we still need to get there, but that would be a very natural thing to do, because I mean SU4 would be with just a single layer, because you have the valley and the spin, and then you would have the 8. My question on all this, of course, is how much it will agree with bilayer systems or not. Is that here the SUN symmetry, we will have it strictly enforced. How strict it is in such systems or in the phases that they see, I'm not sure. Yeah? So I think this is actually a nice point, because then we can see what happens if you have the perfect symmetry, and we could also try to break the symmetry and see what happens. So I would be very interested in discussing a bit more what you think is the nice phase to look at there.
Sure, thanks.
Hi. So in the beginning, you presented quickly that there are these different like strontium lab, Rydberg lab you are working on, and you mentioned for the Rydberg lab like especially to simulate Gauss theories, that you have in mind specific features or something which I guess will be different from the standard Rydberg platform. Mm-hmm. For example, so which would be these specific features you will focus on?
So overall, the very big challenge in the community is to scale up the simulation of gauge theories from one dimension, where we know how to do things. I mean, also in my group, in one of the experiments, we made some specific type of gauge theory. In 1D, yes, it's not too hard to do things. To 2D, because 2D is hard, because you need these so-called plaquette interactions, yes, and that gives these non-local terms that are hard. So our route to that is to go to this Rydberg gadget direction, to encode the gauge theories into spin models, but the spin models not encode into the ground and the Rydberg state, basically, okay, but encode the spin into the position of the Rydberg atom in an ensemble of tweezers. Yeah? So in the simplest case that we have in mind, where we want to work, it's basically you will have a lattice of 2 sides of double wells, basically. And then whether the Rydberg atom is on the left or on the right, that would make the spin. And then that gives you an Ising model, but where you can tune the parameters much more, because you can play with the distance between these atoms and the distance between the other atoms. So it was shown that with that, it was shown by Actually, the first author of the paper is Alessio Celli, with whom we have many collaborations, but this was a paper that they did together with the group of Misha Lukin when he was in the group of Peter Zoller in Innsbruck. So what was shown is that then you can engineer more complicated blockade conditions. Normally, in Rydberg atoms, you have some symmetric blockade, but if you do this thing, you can get more complex blockade with more complicated geometric dependency, such that you can engineer these plaquette interactions in a way that is not too hard experimentally. There were even more proposals afterwards in going beyond just 2 atoms for the gadget and putting 3 or putting 4. So it's very much in the direction of things that Gerard was mentioning in his optimization talk, but here for the goal of simulating gauge theories.
Okay, thanks.
Okay, we're out of time. Let's thank Leticia again.